AI is everywhere. Tech-savvy hospitals deployed in the OR to assist with surgery. Vision systems enable self-driving cars like Waymo and Zoox to safely navigate public roads. And if AI could win a Nobel Prize, it would have gone to AlphaFold in 2024 for predicting protein structures. If you ever wondered how AI works, you're in the right place. Welcome to the Data in the Story, where we deploy curiosity as our defense and offense in a fast-changing world. I'm CJ Washington. This is the first in a series of 5 primers that explores how AI learns. Many Data in the Story episodes, from AI in the courtroom to colonizing space, will touch on AI. And to better focus on the big picture, I'll send viewers here for details about how AI works. This primer will provide the foundation for understanding artificial neural networks. I chose to focus on artificial neural networks for 2 reasons. First, where hype meets AI, there's likely a neural network. They underpin many of the technologies currently generating excitement. Second, since artificial neural networks were inspired by the human brain, they present an opportunity to compare how AI learns to how humans learn. The next 4 primers in this series will cover supervised learning, unsupervised learning, reinforcement learning, and large language models. Learning is the foundation of success in life. And I'm not just talking about getting into the right college. Marine mollusks on the ocean floor must learn to avoid predators. Lions teach their cubs what and how to hunt. The long-term spatial memory of elephants is crucial for finding water in droughts. And humans have the longest childhood of any primate, probably because we have so much to learn. Computers far surpass biological nervous systems in their ability to process, store, and retrieve data. But without AI, computers can only do tasks that can be described with precision. Writing a program to display your friend's face is easy because the screen location for each pixel can be delineated, and the color of each pixel can be set using 3 values to denote the contributions of red, green, and blue light. Writing a program to recognize your friend's face is hard because, well, how do you recognize your friend's face? That isn't a rhetorical question. Let's try to answer it and along the way illustrate how human neurons learn and encode information. That will position us to better understand and contrast how artificial neural networks learn and encode information. The fundamental building block of the brain is the neuron. Neurons are connected to one another by synapses. Neurons receive input from other neurons, and based on that input, they fire or don't fire. It's that simple, and yet, when millions of neurons are organized into a complex structure, they're able to work together to accomplish amazing things. I'm going to name 3 areas of the brain. They aren't the only areas of the brain that play a role in familiar face recognition, but they're the main players. Remembering their names isn't necessary. The important thing to know is that memories are distributed throughout the brain. Storing and recalling them requires different brain regions to work together. The Fusiform Face Area, FFA, stores the visual representation of faces. Every face you see stimulates a unique pattern of activity in the Fusiform Face Area. By activity, I mean neurons firing, and thereby exciting other neurons to fire. These patterns are refined over repeated exposure to a face. You see your friend's face from various angles. Your friend might be wearing a hat one day, or sunglasses, or both. The lighting varies depending on the environment. You're not storing different snapshots as much as you're creating what's called an invariant representation. Your representation is homing in on the core features of the face and filtering out irrelevant details like shadows or makeup. Critically, through repeated viewings, the neurons involved in the pattern are getting better at firing together. This happens through a strengthening of their synaptic connections. Fundamentally, brains learn by forming new synaptic connections between neurons, as well as strengthening existing ones. Later, we'll see a corollary to this in artificial neural networks. You can recognize your best friend's face quickly, even in poor lighting, even when it's partially occluded, because the neural activity in your FFA that represents your friend's face is highly tuned. But this isn't the end of the story. When you see your best friend's face, emotional memories are automatically triggered. These are stored in your amygdala and again are encoded by a pattern of neurons firing together. You probably feel comfort and happiness when you see your best friend. This is your FFA and amygdala working together to create an experience. The biographical details about your best friend are stored in your anterior temporal lobe, or ATL, as well as other brain regions. A unique pattern of neural activity is coordinated across these regions, enabling you to recall your best friend's name. Perhaps you remember that their birthday is the following week and you've yet to make plans to celebrate. A different familiar face would generate different activity in these same brain areas, and you would feel different emotions and recall a different name. And just a quick word about name retrieval. It tends to be especially challenging, not only because most names carry no meaning for us, but also because it requires the recruitment of language areas, which are more vulnerable to disruption due to the precision required. Like biological neurons, the output of artificial neurons is determined by the input it receives from other neurons. Also, like biological brains, artificial neural networks learn by adjusting the strengths of connections between neurons. Instead of synapses, these connections are called weights. A weight is simply a number that signifies how much influence a neuron has on a neuron it's connected to. To make it concrete, imagine that neuron B is connected to neuron D. Information flows from B to D. If the weight of their connection is 2, neuron B's output will be multiplied by 2 before it is received as input by neuron D. If we adjust the weight to 4, neuron B's output will be multiplied by 4 before it is received as input by neuron D. Increasing the weight of their connection increases neuron B's influence on neuron D's output, which brings us to another difference between biological and artificial neurons. As I mentioned earlier, biological neurons either fire or don't fire. There is no fractional output. This same scheme can be simulated in artificial neurons, but it doesn't have to be. An artificial neuron always outputs a number, but it doesn't have to be 0 or 1. Before we put neurons B and D away, let's complete the picture of the artificial neuron. In a neural network, the input to neuron D would come from more than one neuron. The outputs of all of these neurons multiplied by their weights would arrive at neuron D together, and they would be summed, forming the input to neuron D. Let's add neuron C to our example. Neurons B and C are both connected to neuron D. The output from neuron B is multiplied by the weight connecting B to D, and the output from neuron C is multiplied by the weight connecting C to D. These two products are summed, and they become the input for neuron D. At this point, two things are missing. The first is the bias value. Every neuron that isn't part of the input layer, we'll define the input layer in a moment, has a bias value. After we sum the inputs coming into neuron D, we add the bias value belonging to neuron D. If the input coming from neuron B is 6, and the input coming from neuron C is 4, and the bias for neuron D is 0.5, we will sum the input and add the bias. 6 plus 4 plus 0.5 equals 10.5. Like weights, bias values are learned parameters. The next primer on supervised learning will explain in more detail what it means that neural networks learn by adjusting the values of their weights and biases. For now, just remember that the knowledge a neural network possesses is stored in its learned parameters. The second missing piece is the activation function. The activation function is the math or processing that happens inside of a neuron. The sum of the inputs to neuron D plus the bias value determine what the final input to neuron D will be. The activation function determines what neuron D's output will be. As an example, a simple activation function called ReLU, rectified linear unit, outputs a 0 or the value passed to the neuron, whichever is greater. So if a neuron receives -1, it outputs 0. If it receives 1, it outputs 1. The bias adjusts the neuron's threshold for activation. A high positive bias predisposes a neuron to output a positive value, while a lower negative bias makes the neuron less reactive. Before we get into the structure of artificial neural networks, let's talk about input. In the brain, information is transmitted through electrical signals. There are also chemical and mechanical signaling, but our eyes convert light into electrical signals. Our ears convert sound waves into electrical signals. You get the idea. Everything in the environment that can be sensed must be converted into an electrical signal for our brain. In artificial neural networks, information is transmitted through numbers. Thus, all input, images, text, audio, must be converted to numbers before a neural network can process it. Specifically, the input to a neural network is a vector of numbers. For our purposes, we can think of a vector as a list of numbers. There are more to vectors than that, and if you want to dive a bit deeper into the math, I'll provide a resource at the end of this primer. How do we go from an image to a vector of numbers? You probably know that an image is made up of pixels. If you're watching a screen right now, we might start with the pixel in the upper left corner. That pixel can be represented by three numbers, RGB. The first provides the intensity of red light, the second provides the intensity of green light, and the third provides the intensity of blue light. These three numbers determine the color your eyes perceive, and they are the first three numbers in our vector. Next, we move one pixel to the right. Its RGB values take the next three slots in our vector. We do this until the entire image is represented as a vector. Converting text to numbers is a bit more complicated. First, text is broken into tokens. In simple terms, a token is a subunit of a sequence. It could be a word, and we can use spaces as a delimiter to break the text into chunks. A token could also be a 3-character chunk that includes spaces. This is called an n-gram tokenizer, where n is the number of characters in each chunk. N could equal 2 or 5. Tokens don't have to be fixed length, however. In the primer on LLMs, we'll discuss subword tokenization, which uses frequency and reusability to find an efficient and meaningful vocabulary. The vocabulary is the full set of tokens the model knows. Once our text is tokenized, we can assign a number called an index to each token in the vocabulary. We aren't done yet, however. The index numbers don't convey meaning. They simply serve as a key for speedy lookup. A meaningful vector that represents a token is called an embedding. Neural networks learn these embeddings during training. I told you to think of vectors as a list of numbers, but I alluded to the fact that vectors are also mathematical structures. I won't go into the math, but I want you to know that vectors can be similar to other vectors or different from other vectors on a continuum. You can also add vectors together to get other meaningful vectors. For example, the vector or embedding representing the token queen will be closer in vector space to the embedding representing the token woman than it will be to the embedding representing the token sky. When I got my first data science job, Word2Vec was all the rage in natural language processing. Word2Vec is a neural network that learns embeddings of words. Whenever I talked about it, I gave the famous queen-king example. In a well-trained model, if you subtract the embedding for the token woman from the embedding for the token queen and add the embedding for the token man, you will get the embedding that represents the token king. Queen minus woman plus man equals king. It blew me away at the time. This was before ChatGPT. Sound input is even more complicated than text. Sound can be converted into a spectrogram, a visual representation of sound, and then inputted as an image. It can also be translated into numbers through complex transformations that are beyond the scope of this primer. Now that we've covered the different types of input, let's engineer a feature vector for an illustrative toy problem. We want our neural network to predict the probability that a YouTube video is generated by AI. If we wanted to do this in real life, we would give a neural network a bunch of videos, some human-made, some AI-generated, and we would let the neural network discover the important features. Features are the input that the neural network uses to make predictions. In our toy example, we are going to choose 5 features that we will pass to a neural network. Those features are blink rate, the number of times the presenter blinks per half a minute, speech error rate, sync delay, the number of milliseconds between a lip movement and the sound, rate of micro-involuntary head movements, AI might be a little bit still, and video category. Video category will have 3 categories: education, news, and comedy. Every video we give to our neural network will be represented by a vector holding those 5 values. And because the values are already numeric, no conversion is necessary to store them in our vector. We will probably want to normalize the input to ensure the numbers have the same scale. We don't want the 250 millisecond delay to overwhelm the 7 blinks, but we'll assume that has been done. Video category is a bit tricky. We could assign 1 to education, 2 to news, and 3 to comedy, but that would risk creating ordinal bias. The neural network might treat news and comedy as similar because 2 is close to 3, and education and comedy is different because 1 is farther from 3. To avoid this, we will use one-hot encoding. We will add 3 slots to our vector, 1 for education, 1 for news, and 1 for comedy. A news video will have 1 in the news slot and a 0 in the others. That brings our total number of features to 7. To recap, input to a neural network is always a vector of numbers. With that understanding, let's move on to architecture. Artificial neural networks are arranged in layers of neurons. The first layer is called the input layer. Just as it sounds, it receives input. We're building a neural network to predict the likelihood that a video was generated by AI, and each video is represented by 7 features, so the input layer will have 7 neurons. Each neuron will accept a single value. The layers between the input layer and the output layer are called hidden layers. We see the input go into the input layer, and we see the output come out of the output layer, but the internal layers are hidden. The neurons in the input layer are connected through weights to neurons in the first hidden layer. In a fully connected model, each neuron in a layer is connected to each neuron in the subsequent layer. Recall that weights control how much influence a neuron has on the neuron it feeds input to. Say our neural network learned that speech error rate reveals nothing about the probability that a video is AI generated. In our trained neural network, this knowledge could be encoded by adjusting the weights extending from the speech error rate neuron to near 0. In this case, it wouldn't matter what the speech error rate is. The input would always be multiplied by 0. I say this in the context of a toy problem to illustrate a point. In reality, neural networks are complex, and I wouldn't expect knowledge to be encoded so neatly. They're called black box models because the meanings of the weights are notoriously difficult to interpret. It's an active area of research called explainable artificial intelligence. Input goes into the input layer and is passed through each hidden layer until, fully processed, it reaches the output layer. What do I mean by processed? All of the stuff we talked about earlier. Values are multiplied by weights and summed with the outputs of other neurons. Biases are added. And that total sum is passed through an activation function, creating a transformed output. Since we are predicting the probability that a video was generated by AI, we could have an output layer with 2 neurons or 1 neuron. If we decide on 1 neuron, it could use a sigmoid activation function to produce a probability. If we choose 2 neurons, it could use a softmax activation function to produce 2 outputs that sum to 1. One of the outputs will be the probability that the video was generated by AI, and the other will be the probability that the video was not generated by AI. We've covered the architecture of artificial neural networks, their inputs, and how they process data. In the next primer on supervised learning, we'll see how artificial neural networks use label data to adjust their weights and accomplish learning. As you've seen, artificial neural networks are loosely based on, if not constrained by, the architecture of the human brain. If you're interested in learning about the origins of biological intelligence, I recommend The Deep History of Ourselves by Joseph Ledoux. Ledoux is a neuroscientist, and The Deep History of Ourselves tells the 4 billion year story of how we got conscious brains. That's the subtitle of the book. Be warned, Ledoux dedicates a large portion of the book to evolutionary biology. He starts with prokaryotes, the first single-cell life forms. From there, he progresses through jellyfish and early vertebrates. Needless to say, it's a long, if interesting, road to the type of intelligence we discussed here. If you want the full story, I found it fascinating. I recommend reading it. Otherwise, you might want to find something that gets to the point. If you want to dive into the math of AI, I recommend Why Machines Learn by Anil and Nathan Swamy. It's part narrative, part math book, as he wanders through the progression of AI as a discipline, building an intuition for the math along the way. This book is ready-made for two categories of reader. The first are people with a quantitative background. Maybe you're an engineer or a physicist and you want to know how math is applied to AI. You'll find this book entertaining. The second category is people like me. You learn the math of AI in school, but you were cramming for tests and constantly stressed over trying to find a bug in your programming project because there's always a bug in your programming project, and now you want to savor the math. If you haven't formally studied math, but you want to learn it now, this book can be great for you also, but you might need a little help. It isn't a book you'll keep on your nightstand and read for 30 minutes every evening before bed. I recommend going through the book carefully and pausing often to check your understanding with AI. Use your favorite chatbot, Claude, ChatGPT, Gemini, to create practice problems for you or ask you test questions. If you use AI as a tutor, there are two potential problems you'll want to get ahead of: hallucinations and sycophancy, the tendency of AI to agree with you even when you're wrong. We'll discuss AI sycophancy in more detail in the primer on LLMs. Here is a sample prompt to mitigate those issues. Act as a Socratic peer. We are studying the mathematical foundations of machine learning together. Use the source material I specify as our shared ground truth, not your memory. When I explain a concept, don't validate me reflexively. Identify nuances I missed or push back with a counterexample. Prioritize pedagogy over encouragement. If a mathematical step seems leapfrogged in the text, stop and derive it with me before moving on. Periodically, without warning, ask me to re-explain something we covered earlier to test that I retained it. Ask probing questions before giving answers and encourage me to predict the next step before providing the result. Letting the AI know you want pushback and nuance reduces sycophancy, and framing its role as a Socratic peer takes the pressure off of the AI to provide an answer, reducing hallucinations. A system prompt can't resolve these problems, so set ground rules for yourself to ensure rigor. Verify everything AI tells you against a reliable source. Consistently ground the AI with your learning materials. Instead of asking it to explain the bias variance trade-off, give it a paragraph from the text or provide your own understanding. AI is a much better editor than primary source. To remind the AI you want pushback, explicitly ask what nuance you're missing or where your understanding can be sharpened. And finally, check your understanding across various AI platforms. This book is a lot of work, but if you want to learn the math, it's well worth it. I should note, the original publication didn't cover transformers. If you're interested in the theory underlying ChatGPT, Claude, and Gemini, you'll want the paperback edition, which includes an afterword on transformers. I'll include a link to the book in the description. As you embark on your AI learning journey, especially if you opt for depth, I want to leave you with this. AI is a complex topic, and it takes time to learn. If you want to understand how these algorithms work and it feels daunting, don't be discouraged. Be patient. Expect to spend a significant amount of time exploring but not fully understanding the concepts. Learning is a gradual process, and in my experience, understanding comes in fits and starts. When I took Introduction to Machine Learning, I sat in an auditorium and I listened to every lecture even though I felt like I didn't understand much of it. I did well in the class, but I didn't realize how much I learned until things started to click in my upper level courses. Hearing the same concepts explained multiple times in various ways is magic. So trust the process, learn in small doses as often as you can, and in time the magic will happen. Keep your curiosity strong, and whatever you're curious about, I hope it leads you back here and I hope you find what you're looking for. Do you want to know how supervised learning works? Or maybe you're asking, what is supervised learning? Subscribe, turn on notifications, it's coming to the data in the story.